Williams, who was born in Chicago, Illinois, and attended University High School in Sacramento, California, where he later went to pursue his bachelor's in geology at Oberlin College to finally obtain his PhD in geosciences at Brown University. He came to Madison in 2004 and is here today to talk about the ecological responses to climate change since the last ice age. Please join me in welcoming Professor Williams to Wednesday night at the lab.
Great. Thank you all. It's really a pleasure to be here. I do have degrees in geology and geosciences, and if you're paying attention, I'm now a professor in geography, which has confused my family to no end. They can never quite remember which geo am I on any given day. But the reason for that is, as you'll see, that I really do a fairly interdisciplinary kind of work. I study species responses to climate change, so ecology, climatology, using the geological record and using the sediments we can find in the many lakes and mires around us as archives of past ecological and climatic history. So just that opening slide there gives you a bit of a sort of a taste of the scales that we're going to be working on, looking from the last ice age, 21,000 years ago, the last glacial maximum we call it, when we had ice sheets sitting over North America. Right here where we stand was under ice, and then those ice sheets retreat. And as temperatures rise, as CO2 levels, carbon dioxide levels in the atmosphere rise, various species move north. And so one of the things that we use this time period quite a bit for is studying ecological dynamics in a warming world, which has obvious comparisons to what's happening today. So sort of a four-chapter structure here. Give a bit of an intro first here, then move into understanding a bit more about how we use the past to gain insight into ecological dynamics and make preparations for what's happening now and is expected to happen in the future. Give an overview of some of the key lessons we've learned along the way, and then finish a bit on this crossover from paleoecology, which is the field of study that I'm representing here, to conservation biology. How do we make informed management decisions given this kind of information from the geological record? So to start with and to give an overview of, if you think, again, in sort of this context of a changing world, rising temperatures, rising carbon dioxide concentrations, carbon dioxide now at 400 parts per million, which we haven't seen since the Pliocene, and it's still going up. So if we then think about the fact that we expect temperatures to rise and other kinds of climatic changes to go with that, we then start to ask, how can we best conserve species of concern, biodiversity, ecosystem services, all kinds of things that you might want to adapt and manage under these changing climates. And in ecology, we can think of some general areas of risk that might come with those changing climates. So the first one is habitat loss, that if there are species that are endemic to, dependent upon, the best competitors in, highest rates of population intrinsic growth under certain climate regimes, and those climates disappear, then we would expect those species to maybe shrink in population size, perhaps even be at risk of extinction. Sometimes this is called the top of the mountain problem or the polar bear problem, because polar bears are very charismatic species that are dependent upon Arctic sea ice as a key habitat, and as that Arctic sea ice melts back, there's concerns about polar bears having their habitat diminish. No one actually thinks, as far as I can tell, that polar bears will go extinct, but we do think that they'll have reduced population sizes and so forth. Then we have fast rates of change. If climates change quickly, if there are rapid rates of temperature rise over the coming decades, and there's scenarios being, say, 2 to 4 degrees Celsius, temperature rise over the century, that's pretty fast. And the question becomes, how quickly can species keep up? And so there at the far right, as you can see here, is some different estimates of rates of, let's see, I'm looking at my cursor there. So we have these different bars here representing the rate of dispersal ability or mobility of different species. How far can they move in sort of typical sort of populations, kilometers per decade? Some species can move quite far. The large animals have high mobility. Some species, the trees, can't move at all. They have to throw propagules out and reseed and move that way. So they don't move as fast. And then the various lines there represents spatial rates of climate change, converting these estimates of temperature change in any given area to how far will thermal zones move laterally. If you're a tree, if you plant trees, you may look at the Arbor Day, and there are maps of plant hardiness maps those plant hardiness zones are expected to shift as temperatures rise, and species will need to move to keep up with those shifts. There's also the question of rapid and abrupt changes. So the first point two there was fast climate drivers, and can species keep up? There's also the question of fast ecological responses. Will species respond non-linearly? Where are the tipping points? And so there's, this idea that there might be multiple stable states represented conceptually by those balls there, and that you might have one stable state, like a grassland, and then you might push the system hard enough that it flips another state, like a forest. So there can be sort of back and forth between these states. Down in the lower right there, we have different parts of the world. That figure looks a little washed out from here, but that's a map of the world, and those colored areas are different regions of the world where we have observed system dynamics in the past of these sort of abrupt shifts. The Saharan desert in Africa, North Africa, shifting pretty quickly back and forth between a grassland state and a desert state. The North Atlantic circulation flipping on and flipping off, speeding up and slowing down. There are some parts of the Earth system that seem to show this kind of bistability, these quick flips in state. And then the part that I have actually worked the most on, and to some degree I'll develop all these a bit more as we go forward, but the part that I've worked on the most and will develop the most here is this novelty challenge, sometimes called the bottom of the mountain problem, where at the top of the mountain, if you sort of look at that cartoon there, that cartoon is supposed to represent sort of thermal zones, cold, bluest at the coldest at the top, warmest at the bottom, and then in a warming world, those thermal zones move up slope, that those coldest environments at the top move off the top of the mountain and disappear, which is bad news for those species. But the bottom of the mountain has warmer than present conditions that has ever been seen at that mountain before. So now there's new climates that have not been seen at that location before. And the question becomes, how will species behave or respond to those warmer than anything seen at present conditions? Or I'm focusing on temperature here, but there might be other dimensions of climate, more extreme precipitation regimes, events, and so forth. This is called Novelty. And there's a map right there sort of mapping out globally areas of high climate novelty. This is a paper we did about 10 years ago now. And we did a sort of analysis of 21st century climates by the end of this century versus climates at the beginning of this century, and identified places where the climates of the future had no close counterpart in the climates of today. And they tend to occur in the tropics and subtropics, the warmer world, and those parts being at the leading edge of a warming world. Becomes a question of how well can we predict how species respond in anything that's to climates that are warmer than anything we see at present. So that's the setup, and these are all kinds of questions that are ecological questions today, and not coincidentally, they are ones that can be addressed by looking to the past. And that's a big part of what I do in my work, is trying to work with geological data and the geological record of past climatic and ecological events and draw parallels and insights into what's happening today. So in this picture here, what we're seeing now is changes in temperature on the vertical axis, and this is expressed as relative to the late 20th century, like 1960s, 1990s or so, and positive values will be warmer than that reference point, negative values will be cooler than that reference point, and the time scale is a little tricky here. It actually changes its scaling. And this line here, if I get my cursor back, represents today. This is looking out 100 years in the future. This is looking back over the last 150 years. So this would be back to about 1860 or so. This is basically the domain for which we have weather station data, instrumental data, direct observations of the climate system and its changes through time. And what we see is that there's been a rising trend in temperatures with some little stair steps along the way. And we expect these trends to continue, and this is being driven by the rising greenhouse gases from our fossil fuel and land use and land cover change through the emissions of greenhouse gases, carbon dioxide, methane, and nitrous oxide primarily. We go further back in time, we can see there's been some variations back here, but you can see that over this time scale, we've had a range of variation of plus or minus a degree or so, but nothing like what we expect to see over the next century. And this is now going back to about 10,000 years ago. So this is now back to 2000, the scale's changing here, and back to about 10,000 years ago. So this is a common challenge we face, and I'm focusing on ecology, but you can sort of extend this challenge to any area of the world. How do economic systems behave? How will flood regimes in the greater Milwaukee area behave? This general challenge of we're moving the system into a state that's not like anything we've seen in recorded human history, and how do we best adapt and plan? So In this challenge, we have sort of, if you're a scientist trying to tackle this, I think it would be fair to say you have 4 general classes of tools. You can do experimental manipulations, and these are from the Department of Energy's free air carbon dioxide enrichment experiments, the FACE experiments, where they built towers around forest plots and agricultural plots and grassland plots, pump CO2 into those areas, and then watch how the forest or other ecosystems behave under enriched ambient CO2 levels. There's other kinds. You can do warming experiments and so forth. We have numerical models and computational models that model the atmosphere and the oceans and the other part of the cryosphere, the ice sheets, and how they behave under rising temperatures or other changes of rising greenhouse gases and forcings the climate system. You can go to modern analog systems such as deep sea vents there. People are using deep sea vents to study ocean acidification because there's a lot of those, that's very acidic water in the vicinity of those deep sea vents. So if you want to know how deep ocean communities will behave under rising CO2 levels and the rising CO2 concentrations that will permeate into the oceans, that becomes a system you can study. And then the part that, again, that I'll develop further here is going to the past and looking for geological time periods that have some counterpart to today. So to take that same diagram now, and that's the same one I showed 2 slides ago, and now expand it out. So now we saw the last 10,000 years, which is here, and now I've extended out the last 5 million years, and so this is going back to 500,000 years ago and back to 5 million years ago. And now you can see when you sort of zoom out a bit further, there's all kinds of climatic events happening that have some interesting parallels and are good model systems for what's happening now. And some of the key features you can see is that you can see there's a slow drift of the Earth system towards a cooler state over this sort of 5 million time period. And then you can see that over the last 500,000 years, there's been this very pronounced glacial interglacial cycle, and I'll return back to this in a little bit. But we have these warm periods, cold periods, warm periods, cold periods, and these are pretty abrupt transitions. And I'll zoom in to show you that some of these transitions are similar in rate and magnitude to what's expected over here. And so obviously, this is a cooler world than we're expecting to have in the future, but the rate of change and the amount of change is comparable from those time periods to what's expected this century. So now to go into that just a bit more here, so now to kind of go from that framing to actually talking a bit about these geological time periods, this is another version of this data here. This is what's confusing and annoying about my field is that we aren't consistent about which way time goes. Time is running from left to right in this plot. Now it's running from right to left, so that's older over there, and it's younger over here. So that's 1.8 million years ago at far right to today. We also, being geologists, we count back from the present, so that's 0 years ago at left and 1.8 million years ago at far right. So what you see when you look at this is that there is this very regular climate variation. This is one of the really cool things that got me excited about paleoclimatology when I was a grad student starting to learn about it, is that there's this very regular oscillation in the Earth system between what we call the interglacials, the warmer periods with smaller ice sheets, and the glacials, the colder periods with larger ice sheets. And you can see at far lower right there, the ice sheets covering North America during a glacial period and parts of Eurasia as well, and then the interglacial, like the one we're in right now, with ice sheets restricted to Greenland and Antarctica. So we have this regular oscillation, and if you actually were to do a periodicity analysis, you would find out that there's a 40,000-year beat back before a million years ago, and it shifts to about a 100,000-year beat, that those big cycles are happening 100,000 years ago, or every 100,000 years, and then they shift to a higher frequency back before. Why it goes from 40,000 years ago to 100,000 years ago is an area that people are still working on, but we know in general that all that periodicity is being controlled by variations in the Earth's orbit, that the Earth's orbit varies at these time scales. It changes from being more circular to more elliptical. That's what that diagram there shows. The tilt of the Earth changes from being more closer to perpendicular to further away from perpendicular. We wobble like a top wobbles. And those 3 components of motion, the eccentricity, the tilt, and the wobble, which we call precession, affect the amount of sunlight we get at different latitudes. That changing the amount of sunlight we get at different latitudes and seasons directly controls how the growth and melting of those ice sheets and other parts of the climate system as well. So we have a very good understanding of this orbital, we call the orbital variations, the orbital forcing of these ice ages and they're waxing and waning. Okay, but this isn't a paleoclimatology talk, this is an ecology and biogeography talk. So this is really the structure that as an ecologist we're working in. What we're interested in less is what's causing these climate variations, but how do species and ecosystems respond to them and survive them? Because if you're a species that's been around for any more than a few 100,000 years, you've had to live through multiple glacial and interglacial cycles, and you've had to be able to adapt to and accommodate this kind of climate change in the past. So now what I'm going to do is to zoom in into just one of these events that's the best studied of them all, because we have lots of lakes and mires and radiocarbon dated sediments that cover it. And so this is the last deglaciation. This is the last transition from the last glacial maximum to the current interglacial, what we call the Holocene. So now we're looking, time is now going that way again, oldest 22,000 years ago to present at far right. Time scale is, or vertical scale is again temperature as difference from present. So this is a record from Greenland. So this is telling us that Greenland was about 10 degrees colder than present about 20,000 years ago, and that about 10,000 years ago it reached more or less modern day or pre-industrial revolution temperatures, and it's been more or less constant there ever since. And what you can see is, of course, you can notice very quickly that it's not just a little linear ramp up. There's some very abrupt changes along the way. There's some very distinct events, and we have given them names. We call that first abrupt warming the Bowling warming as part of a broader event called the Bowling Alerode. And then there's that Younger Dryas, which is that return to sort of near glacial conditions, and then the abrupt end of the Younger Dryas, which is the start of the Holocene, the start of the current interglacial. So lots of things are happening climatically. Globally, temperatures rise by about 4 to 5 degrees Celsius. Some of those changes are what we would, sometimes as your geologist say, oh, things happen really fast in the past, and people say, oh yeah, you're a geologist, you're talking about millions of years, that's not meaningful. These are really abrupt, even on human timescales, that people think, based on these Greenland and other high-resolution records, that some of these abrupt shifts in the climate of these areas could have been 9 to 14 degrees Celsius in 1 to 40 years. In our own lifetimes, would have been sort of the comparable kind of rate of change. So these are big past climatic events. These aren't global, these are North Atlantic, Western Europe, but in these areas, at least some regions, we've had very rapid changes. Ice sheets melt back over this time period. That plotted upper right is showing this, I think this really beautiful diagram of the Laurentide ice sheet and the Cordilleran ice sheets. The dark blue is its furthest extent, and then it's melting back over this sort of from about 19,000 years ago to about 6,000 years ago. The ice sheets are wasting away as temperatures rise. Sea level rises because that water's got to go somewhere and it winds up in the world ocean. So that's about 400 feet or so of sea level rise from the last glacial maximum to present. And then novel climates emerge. And what I mean here by novel climates is that if you actually look at the ranges of climates that occurred at some points in the past to the ranges of climates that happen today, there are areas of non-overlap. And the way to kind of show that visually is at that far right plot there, where what we're looking at here is just two simple temperature axes, summer temperatures and winter temperatures. And we're looking at each location that represents some location in North America for 3 different time periods. Red being a projected forward set of climate model simulations for what we think North American climates might look like maybe 30 or 40 years from now. Black would be the late 20th century, the recent past. And then blue is 15,000 years ago. And what you can see is that there's areas of non-overlap. I don't know how well you can see it from your angle, but there's an area over here, for example, whereas we move into a warming world, portions of climate space open up in North America, these novel climates that aren't available to species in North America today, presumably mostly in southern parts of North America. Whereas 15,000 years ago, there's a whole other portion of climate space that opens up back then. This portion of climate space is more seasonal. We have kind of warmer than present or similar to present summer temperatures and colder than present winters. And the reason for why we have this sort of portion of climate space open in the past that's not open today is because of these changes into Earth's orbit and the way that it affects temperature seasonality. It actually has different effects upon summertime temperatures and insolation, incoming solar radiation, and wintertime values. So that opens up portions of climate space that species had available to them 15,000 years ago that they don't have today. Okay, so that was all sort of setting the stage and setting the context here. Now to go into, okay, now we have kind of some understanding of these times and places. Let's go into how do we sort of study these time periods. So this is kind of the starting point for the data we gather. We go out in the field and we get muddy. We go out into the middles of mires. We set up floating platforms on lakes, and we take long tubes of mud from those sediments. Here's a cleaner looking team actually out on a lake here, and this is from Horseshoe Lake just outside of St. Louis by Cahokia. If you've ever been down to Cahokia, we were working right outside of Cahokia there, and getting a record of environmental and vegetation history from Cahokia. And so you can see that maybe there's a couple of steel tubes there, but it's about a meter long steel collection barrel that we drive down a drive at a time, bringing back up a meter of mud at a time. And as long as that lake has been around, it's been collecting mud, and so we can take those cores of mud back to the lab and analyze them. So now we're extruding that core of that long tube of mud. We're going to wrap it in those. We're going to first wrap it in cling wrap, and we're going to wrap it in those PVC. It's got kind of a consistency of kind of a banana at the top, down to pencil eraser at the bottom, as the bottom sediments get more and more compressed and dewatered by the weight of the above sediments. So it has some cohesion and stability to it, but we wrap it up and protect it and take it back to the lab. So there here's another one where before we've wrapped it, just getting a quick photo of it, and you can just see that some of these sedimentological variations. This is a lake that has dried out, obviously, at some point. So you can see how the uppermost sediments that left have become oxidized. They've been exposed to oxygen. They're getting kind of rusty and iron-rich, whereas the bluish sediments at right, that's reduced iron that hasn't been exposed to oxygen yet. So just as a first pass visual, you can start to get some insights into the environmental history of that lake. And then the kind of what our field works with is what we call proxies. What we want to know about are past temperatures, where do species live, past water pH, but we don't have thermometers, we don't have species traps or photo cameras. What we have are proxies for these things. So we use pollen as a proxy for the past plants. We use very stable isotopes like oxygen as a proxy for water balance or temperature, and so forth. And different labs work on different proxies. Ancient DNA is increasingly used as a proxy as well. And so my lab does pollen analysis. We're actually celebrating the 100th anniversary of pollen. This is a birthday centennial year. Pollen analysis was was initiated by von Post, a Swede, in 1917. So this has been around for a while. But because it's been around for a while, it's a mature proxy, and it's one that we've gathered a lot of data on over the last century. So we can now work with large proxy networks of different records from different places where people have been doing this kind of work for a long time. So the way it works is that plants produce pollen. Some plants are relying upon wind dispersal, so they throw that pollen up in the atmosphere, and they hope that by chance some of that pollen they throw up there will land on a female flower and perpetuate the species. It's a very inefficient way of doing that, but pollen is cheap, and so they do this sort of broadcast approach. Some of that pollen settles on the lake, settles down through the water column, is captured at the mud at the bottom, and then as that mud accumulates up, the older sediments are at the bottom. They have pollen from when that lake formed 15,000 years ago or whatever, and the uppermost sediments are the most recent sediments deposited in the last few years. We core it, we bring the mud back, and then under light microscopes, and sometimes SEM, scanning electron microscopes, we identify the pollen to genus, sometimes to species, sometimes to family, and there's some just different photos for different pollen grains as you'd see them under a light microscope. So kind of just one quick example of this kind of work. So here's one site in northwestern Indiana where we have beach. And here's one lake sediment record. And what we produce is called a pollen diagram, recording from those lake sediments all the different pollen that we find from different zones. It tells us something about forest history and change at this site. Not only does my field go left to right versus right to left, we also go up and down. So now time is on a vertical axis here, oldest at the bottom, youngest at the top, and that actually makes some sense because that's the way the sediments are deposited. The oldest sediments are at the bottom, the youngest sediments are at the top. So this is kind of how a geologist often sees these things. So each curve then represents the relative abundance. Usually what we do for any given horizon, we might count 300 or 400 pollen grains, identify them with these different tree taxa, and then we say, well, what proportion of those grains we counted were fir or spruce? And so what we can see is, so each curve here represents a different taxa. We can see that in northern Indiana, 15 to maybe 12,000 years ago, there's a lot of spruce around there and a moderate amount of fir. and a little bit later pine comes in. So we can see boreal forests, kind of forests that we'd find in northern Wisconsin, southern Canada. Those forests were occupying northern Indiana 15 to 12,000 years ago. They disappear. Pine comes in. We get a sort of a pine zone for about 1,000 years. Pine disappears. You get oak, that big green curve at near far right. Oak comes in, we get these oak-dominated forests. You can see that beech curve. It's flagged with beech up there. Beech comes in around 7,000 years ago. So you can see these sort of long-term changes in forest history that are being very directly driven by climate change, that as temperatures rise, the boreal forests die out. Those species effectively migrate north. And then other species like oak migrate in and become more abundant. And then a little bit later, sometimes species take a little while to get there. Beech comes in, establishing by what we call the mid-Holocene about 7,000 years ago. So that's just one site. And of course, so one site gives you a lot of information about temporal history at one location. It's also a lot of work. Someone's got to sit there at the scope and count these pollen grains. And so what our community has moved to is creating what we call community curated data repositories. And the one that, oops, hold on. Mosey's nagging me, sorry. Okay. So what we've built are databases to house our data so we can move from sort of single point temporal analyses to multi-point spatiotemporal analyses to look at range shifts and range migrations. This is a resource, the Neotoma Paleoecology database. The URL is there. It's one that I'm one of the PIs involved in building this and helping build both the infrastructure and then the contributing of data to it. And so what this lets us do then are things like this, where now what we're looking at here is an animated map of North America. This is an earlier visualization that goes back to a paper published in 2004. We're working on creating some updated version of this, but it's still a great visualization, so I still use it a lot for talks. And what we're looking at here is every frame is 1,000 years. So we're stepping forward 1,000 years in time. And some of the first things to pay attention to is you can watch the ice sheets retreat. You can watch the ice free corridor open up between the Cordilleran and Laurentide ice sheets. You can watch Florida shrink because as sea level rises, areas of low relief, like the eastern seaboard, lose the most. So Florida is quite large. It loses a lot of land area between the last glacial maximum and present. The west coast, not so much happens. So you can watch sea level rise and ice sheets melt. But then the main thing this is supposed to show here is the forest dynamics and showing how spruce migrates north. Spruce used to be going south of us 20,000 years ago, and its northern range limit was right around here. And then as temperatures rise, the southern spruce populations die out, the northern spruce populations expand into new areas, and the whole population moves northwards. This is some of our best evidence. When we talk about species migrating and moving in response to climate change, it's this kind of data that concept is founded upon. Now, of course, we're starting to see species shift their ranges in response to current climate change that's happening around us now. But the best documented data we have for how species respond to these sorts of long and large climate changes come from this kind of data. So, okay, everything I've shown you has been very data-centric. Out in the field, working with the mud, in the lab, counting the pollen, making maps, straight up from the data. But of course, in the sciences, you really work from two directions. You have the empirical lines of evidence and the modeling or theoretical lines of evidence, and you have sort of the intersection between the two, which is where the interesting science happens. And on the modeling side, a very common tool, there's all kinds of different ecological models out there. A very common one that gets used all the time is what's called species distribution models, SDMs. They're called environmental niche models. And what you basically do is you take some set of occurrences where a species is found out in the environment. Then you overlay that set of occurrences with the environmental characteristics, the topography, the temperature, precipitation, other variables, and you build a predictive model that predicts the species occurrence or abundance as a function of environment, what we call a response curve, the response of a species to that environment. And then you say, well, what if the environment's going to change? What if we have a global warming or some other degree of climate change, using a climate model to give us that scenario? And then you say, well, this is where we think the species would be in the future. So we use this sort of approach all the time to predict how species will respond. Where should we conserve habitat? What's the risk of extinction? Using these kinds of modeling approaches. And just as one example, this is just one of many papers. This is just one synthesis paper coming up with estimates of how many species do we think will go extinct over the coming century in response to the different climate scenarios. So the x-axis is how much temperature rise will there be relative to sort of 1800s pre-industrial baseline, and then what percent of species would be predicted to go extinct. And this is a meta-analysis of many different studies, and they all predict some degree of extinction, some just a few percent, some quite alarmingly 20 to 40%, but there's a fair cloud there. And then some, the red line being some fitted curve to that, and a general sense that the more we have temperature change, the more we stress species, the more we change the environments around them, the higher the rates of extinction. And those SDMs I showed you are part of the backbone that predict these kind of responses. And so one thing, of course, the challenge with this is that we can't test these predictions, right? We have to wait 90 years to see how many species have gone extinct by the end of the century, taking no action in the meantime. That's not a very satisfactory approach to doing things. So what we can do instead as a model testing ground is what we call hindcasting. We can take these models that are usually run from the present into the future and instead run them from the present back to the past and see how well they do there. So this is one set of analyses where we actually ran it forward, but we ran it forward from starting from 15,000 years ago. We said, okay, let's take this model, started from 15,000 years ago before the last deglaciation, before the climate changes that happened, and then say, okay, how well would that model predict where that species would be today? And so here's the distribution of oak at lower left. The colors are kind of ugly, but the greens are areas of high oak abundances. Oak was generally further south in Florida and so forth, southeastern US. And then as temperatures rise, it expands northward. The lower right, the lower right is what's been modeled for its expansion. The upper right is what we observe from the modern botanical and pollen data, and we get a pretty good fit between the two. So this is actually a case where the hindcasting works, where this species distribution model is able to predict a northward range expansion of this set of taxa of this genus in response to climate change. What we can also find out, though, is that if we actually do an analysis of how good was that fit, the correlation between what was modeled and what was observed, and we say how far back do we start the model and then predict it forward, we find that the correlation is pretty good if there's not much time separation. If we take climates from 2,000 years ago and predict the present, we get a pretty good match. And if we go back to, say, climates from 14,000 years ago and then ask the model to predict the present, we're now getting down to a correlation of 0.5 or so. So there is a sense that model performance degrades the further you go back in time, the more climates change between your starting point and your end point. Okay, so that's kind of going to now the modeling side. I'll come back to that with a few slides at the end, or near the end. So, okay, from this kind of work, what have we learned? This is kind of I'll go through each of these in turn here. But talking about we can see that species are clearly sensitive to climate change. We can see that species move in response to climate change. They do so individualistically. And we also see that species that we don't have much evidence of climate-driven extinctions except for the large animals, the mammoths and the other large animals that are probably being affected by a combination of climate and human action. We see this emergence of novel ecosystems in response to those novel climates. And as I'll come back to, this challenge of ecological forecasting. Okay, so I'm going to go through each of those in turn with a few slides. So this question about rates of response, but this really matters. If temperatures are going to rise by several degrees over the century, how quickly can species adapt? Should we be moving species and through what's called assisted migration or managed relocation? So we sit back and let them adapt on their own, let nature take its course, or some set of other options. And so one thing we can see from the paleo data is that when climates change, you very clearly get strong local responses and often very strong fast responses. In this plot here, again, time being vertical now, oldest at the bottom, this record here is a temperature record. So this is going back, remember that Greenland ice core and those fast changes we saw around the Bowling Alleroy and the Younger Dryas? This is one of those events. So there's a very fast warming here. In Greenland, about 9 to 14 degrees Celsius in a few years, probably not quite as big a warming at this location. But what you can see is temperatures rise, and almost instantly, from a geologist perspective, the communities turn over. That you go from a sedge plant community, kind of an open tundra, to a juniper woodland within the span of a few decades. So almost within, very quickly, this plant community is changing and turning over in response to that temperature forcing that it receives. But several centuries later, pine shows up. So there's both what we call the fast responses of sort of local community turnover, and then the slow responses, where pine probably was not anywhere near this site when these temperatures changed. It was probably hiding out in various refugia down in the Alps and had to expand northward to this location, and trees don't get up and move. So it took a few centuries for pine to get there. So we can see that this example we call a delayed response or a lagged response, where it takes a few centuries for the full sort of ecological effect of that rising temperature to be felt at this site. We've already walked through this point, the idea that was at one site, and then we can sort of step back and look at the whole continent and see that species accommodate climate change by moving. They try to stay within their thermal zones or their climatic optima or ranges of tolerance, and one way they do so is by moving spatially as the environments change around them. Moreover, I've only been showing you spruce mostly because it's a nice kind of iconic one, but if you actually start to look at other taxa and start to look at how they respond, what you start to see is that different species respond at different rates and in different directions. And so we can see that that's spruce again, northward shift. We look at ash. Ash doesn't really move much of anywhere. It expands a little bit north. There's a bit of a northward range shift to it. But mostly what ash does is it goes from being not very abundant to being really abundant between 15 and 13,000 years ago, and then not being very abundant again. And so it's a completely different trajectory from what we see from that sort of simpler story of sort of northward expansion with rising temperatures. And notice that today we think of spruce being up in Canada and northern Wisconsin, and ash being parts of southern Canada and the eastern deciduous forests. So we think of these as largely disjunct species from different biomes or ecosystems. But if you've been an ecologist walking the landscapes 15 to 13,000 years ago, you would have thought that spruce and ash that was a normal association. And so the mixtures of species change. We start to mean by novel communities or reshuffling of species in novel mixtures, that as climates change, each species follows its own path, and as a result, you get this mixing and breaking down of existing communities around you and new ones emerging. We should expect the same sort of things to happen in the future. We should expect that because of this, some of these co-evolutionary relationships should be pretty weak. If your neighbors are changing all the time, maybe you're not tightly co-evolved with the other species around you. And so it's starting to think about some of those implications for co-evolutionary relationships. And again, this sort of prediction question. Another point that's I think of real interest is that if you actually look at the last 1.8 million years, even going further back, one thing you don't see a lot of are species extinctions. Species extinctions are there. They're not nothing, but they're not very common either. And you can make a good case that they're not much above sort of what you sort of back to sort of a typical background rate, that species are kind of always coming and going, and that might be sort of typical. And when you do see extinctions happen, they often tend to be at the cold periods, that sometimes species die out either locally or regionally during the cold glacials, but not as much evidence of extinction as during the warm glacials. So there's some sense that there's a bit of asymmetry here where the colder periods are more stressful for species and can drive extinctions more than the warmer periods. This is sometimes called the quaternary conundrum there, because I just showed you a few slides ago these predictions of large rates of 15% extinction rates over the century in response to 21st century climate change, and yet when we look at the geological record, we just don't see that much of it happening. But the obvious counterexample to that, I've been focusing mostly on plants so far, but of course there's these very large animals roaming these landscapes. We used to have mastodons all over the place around here, and those mastodons aren't here anymore. The mammoths aren't here, the camels aren't here, the horses, all over North America. And worldwide, we do have a major extinction event, but it's very much concentrated on the big animals. We lose about 2/3 of all the big animals worldwide, starting about 45,000 years ago up until the recent past. In North America, we lose about 34 genera, and this long-running question about what does them in. And I am of the personal mindset that it is some combination of climate change and human dispersal, right? Humans are moving out of Africa beginning around 100,000 years ago or earlier. They spread into Europe, into the Southeast Asia, into Australia by about 40 to 50,000 years ago, into the Americas by about 15,000 years ago. And interestingly, it's not a perfect correspondence. It's not as if the early hypotheses were this blitzkrieg hypothesis, that when people showed up very quickly, they hunt down the animals. It now looks like there's often a period of coexistence for several thousands of years, but then the animals do die out. And for me, the telling point is that we don't see waves of large animal extinctions during all these previous glacial and interglacial cycles going back the last million years. It's only the most recent one where these extinctions happen. And to me, that's sort of one of the key signals that it's this new factor of climate change plus this new predator, new large animal in the landscape that's causing these extinctions to happen. It's also telling that if you look at which animals go extinct, it's the very large ones. And those bar charts over there are showing the blue, it's rated by body size there. And then the vertical axis is the number of species that go extinct, or sorry, the number of taxa in that body size. And so what you can see is that the red ones are the ones that go extinct, the blue ones are the ones that survive. And so the extinctions are very heavily concentrated on the big end, the animals that would be the easiest to find, the most resources for early hunters to get. So, and the timing and pattern is consistent as well. Okay. So we see this idea of novel ecosystems that I talked about, species, and I'll show in a moment, a good case to be made that these novel communities are forming in part in response to the novel environments that they encounter that exist in the past that don't exist today. And one way of looking at this, going back to this point about seasonality, remember what I showed you at far right there, that 15,000 years ago, climates in the past were more seasonal than they are today. Now look to the far left and look at where ash is found today. And that middle plot here, I don't know how well you can see it, but there is this black set of dots, and there's maybe a little bit harder to see set of gray dots here. This is the climate space of North America. And what this figure should be showing is that we have the black dots is where ash is present in North America. The gray dots is where ash is not present, but those climates exist. And then for much of ash's range, we have some constraints that ash cannot be found in these areas, that we don't find ash in these areas at least. But over here, ash is right up against the edge of the North American climate envelope. It's found right in the middle of North America, which is as seasonal as it gets in North America. So there's some sense that ash could expand into these climates, these more seasonal and present climates, if those were to exist. They don't exist now, but these climate simulations suggest that they did exist in the past. And so some of these sort of spruce ash assemblage and some of these other no-analog communities that form, we think are forming in response to this heightened climate temperature seasonality of this sort of late Pleistocene time period. So one consequence then, as I showed you, oops, I don't have a, oh yeah. So I showed you a map a few moments ago about oak and looking at how oak does. This is another map for Fraxinus. This isn't quite as clean as the other one I showed you ago. But again, here's the modeled distribution of oak of ash 15,000 years ago. We take that model, predict it forward to present, and the model basically thinks that ash shouldn't exist at present or should exist only at very low abundances. Where in fact, we know that ash does exist at present. And so this is a good and the correlation between these two maps is terrible. It's 0.09 correlation. And so this is a good example where the model is not matching to the data and is having a hard time taking these novel climate spaces of the past and then basing predictions on them into the climates of today and the species of today. Just like that oak plot, we saw that, in general, predictions based on more recent time periods do better. Predictions based on earlier time periods do worse. But now, if we look down here, the correlation again is very low. And so basically, what this is telling us is if you take the set of climates of it that we know for 14,000 years ago and the known distributions of ash for 14,000 years ago, build a predictive model based on this data and relationships, that model has little or no predictability to today. And so that is an example of how these novel climates can confound these models because, again, they're statistical models. They're not very good at extrapolation into the unknown. This is a case where they're really breaking down in these sorts of situations. And one more just kind of visualizations around this. This is showing the sort of total climate space in North America 15,000 years ago, the total climate space of North America 1,000 years ago, and then the black dots being the places of high ash abundances. And so what you can see is that this portion of climate space that opens up down here is also a place where we're finding lots of ash. So the ash is really preferentially occupying these highly seasonal climates, these climates that don't exist today. And so, again, this is sort of these signals that as climates change and new portions of climate space open up, species are able to respond to and occupy these spaces, and sometimes our ecological forecasting models have a hard time predicting these novel climates and community responses to them. Okay, so those are some of the lessons, some of the kind of big kind of things we can take away from what we see from the geological record. And now just a few slides at the end about what should we do, what kind of things can we we take this information and bring it to bear on current challenges. In general, if you're thinking about climate change and you're sort of working at a high level, thinking about sort of policy options, there's sort of two general options. One is mitigation, which you try to mitigate or prevent climate change by reducing our greenhouse gas emissions. And the other one is adaptation. We try to increase our resilience to climate change. When I first came into the field 20 years ago, adaptation was viewed as kind of a taboo, that we shouldn't be thinking about adaptation, we should be really focusing our efforts on mitigation. But increasingly, these are really seen as not either or, it's and both kind of situations, because you want to avoid the really high-end climate scenarios that might cause a 4-degree or 5-degree warming this century that would cause all kinds of harm to low-lying areas, small islands, heat waves, droughts, etc., and rates of adaptation for species and so forth. You want to avoid those outcomes, and mitigation does that for you. It moves you away from the high-end climate change scenarios down to the lower-end or middle-end climate change scenarios, whereas adaptation recognizes that climate change is already underway. Climate change is happening. It's been underway for the last several decades, and now it's just a question of how much climate change we'll have, and at what point will we level out or maybe start to reverse things. And so the Paris Accords said we need to stay at 1.5 degrees Celsius, so that would put a limit around here or so. And so there's different scenarios and pathways to get there, but no matter what, there's going to be some amount of climate change and some amount of adaptation needed to those. And so adapt to what you can't avoid. And so if you think about, from an ecological perspective, one thing to recognize is that, again, species accommodate climate change by moving, but that's actually been sort of a hard concept for us. We have legal restrictions in place. We think about invasive species. There's some species you can't move across certain boundaries. And I'm certainly not advocating for wholesale movement of species across continents. We know about all the issues of moving exotic species into places they've never been before. But within continents, within regions, we should recognize that species have moved in the past, and they will move in the future, and doing things like adaptive planning, looking for seed sources from populations maybe not in the current area where you're trying to reseed a species, but to the south of it. So organizations like the U.S. Forest Service are starting to change their guidelines so that instead of simply taking seed from current areas, they start to look for seed sources a bit further south and so forth. Some places, like Alberta, foresters in Alberta are actively planting species outside of their historic ranges in the expectation that by the time those trees come to maturity, 60 or 80 years from now, the climates that they'll grow up in will be the climates favorable to them. And so they're doing sort of proactive planting for future forestry and harvesting. This gets into this topic of managed relocation. And so sometimes if you're worried that a species habitat will entirely disappear or largely disappear as a result of climate change, maybe due to sea level rise or other factors, moving these vulnerable populations, picking them up from one place to north. This, again, can cause concern. I tend to be of the perspective that this is a natural process. It's just one that we haven't seen happen much because we haven't seen that much climate change happen in our human lifetimes. And so this is the kind of thing I tend to support as a way that's congruent with past climate change and past adaptations to it. And also recognize that what we think of as a normal or natural set of species around us may be a temporary phenomenon. Species move, associations come and go, and that as climates change, we should expect these shifting associations to happen in the future. Some species moving faster than others, some species being more temperature sensitive or rainfall sensitive or extreme sensitive, and so we'll expect to see this reshuffling of species. This has led to this concept of novel ecosystems, and there's a bit of an argument about that right now, and there's a couple of quotes about that argument. And so Hobbes, for example, is arguing that novel ecosystems, the concept of novel ecosystems, is based upon the fact of novel ecosystems. He's saying already we can see that that some ecosystems have departed entirely from their historical analogs, whereas others have argued, no, we can keep things in a current state. We shouldn't accept sort of wave the white flag of surrender, but accept these unavoidable and widespread irreversible changes. And so there's been an argument about this. What should we be conserving to? What should we be maintaining? I, again, tend to favor more the former perspective, that these are dynamic systems, that our systems are changing, and we should look for ways to facilitate those changes, one that best promotes biodiversity and the services that we depend upon. And again, we expect that climates are changing, that we expect novel climates to emerge this century. So this is very much a real process for us all to be wrestling with, and that we are wrestling with in the professional sector, and I think it's worth bringing out to the broader community as well. And if we look around, I've been focusing here on climate change, but if you think about it, there's of course all kinds of other factors transforming ecosystems. There's been invasive species, there has been land use and legacies of past land use. So the Parthenian rangelands is an example of a toxic, invasive species that we generally try to limit its spread. Puerto Rico is an example of an area that's was widespread sugar plantations, is now reforesting, and as it's reforesting, it's becoming this interesting blend of native and exotic species, apparently with not major negative ecosystem or biodiversity consequences. If anything, biodiversity may have gone up in some of these areas with this mixture of natives and exotics. Isle Royale is being a relatively pristine area, but one that nonetheless is changing in many ways. And then the Coral Triangle as an area that is changing and is threatened by rising temperatures, ocean acidification, and so forth. And so we can recognize that the world is changing. We can recognize that novel ecosystems are emerging. Some of these we might view as more positive and beneficial. Others we might view as more negative or ones to try to reverse. But nonetheless, we should recognize that we are in this changing world and that we should seek to facilitate certain kinds of change and mitigate or reverse others. Okay, so I've kind of worked through these points here already, but again, this perspective that comes out of paleoecology of the world has always been in flux. Now new changes are happening, we are accelerating the rate of change, and in general, I would say the prudence would dictate that we try to slow down rates of climate change, we try to stabilize the climate system, but we should also accept that change is underway and that those rates of change lead to adaptation needs, and those adaptation needs can be grounded in the lessons from the past. Thank you. Thanks a lot.
You work with pollen in order to explore these past climates. And you've shown that some of the models seem to work fairly well in terms of predicting current distribution, right with the climate. Others work very poorly. What is the state of DNA preservation of those pollen grains, and is there any effort underway to look at if there is DNA extractable genetic changes that may make the difference between?
Yeah, ancient DNA I haven't talked about, but that's because it's multiple talks on its own, and it's really exciting what's happening with ancient DNA. The best ancient DNA, the most promising work is being done in the high Arctic because the rate of degradation of DNA is very temperature sensitive because it's basically microbial broken down, and that rate of microbial breakdown is temperature regulated. So people have found ancient DNA in Arctic sediments going back to 40, even 100,000 years ago, whereas around here in Wisconsin, 8,000 years ago. Tropics, 1,000 years and you're lucky. So this is where the Arctic people really have it best because they can get these wonderful ancient DNA data sets. The other thing that happens with ancient DNA is that even when it survives, it gets increasingly broken down from long chain lengths of really small fragments. We've done some ancient DNA work where you're working with base pair lengths of 30 to 50 fragments or so. So right now, most of the ancient DNA work I've seen has either been species identification. This comes from a mammoth that we don't have a bone from, but we find an ancient DNA fragment from, or population bottlenecks. We look at sort of losses of genetic diversity as a way of looking for past genetic bottlenecks in bison, say, or other species that have good ancient DNA records. The kind of question you're asking, the DNA there's not enough DNA to do that yet. That sort of that adaptation and using the DNA for that kind of adaptive responses, we don't have enough of that kind of work yet. But that would be the next frontier to push to, is look for adaptive genetic frequencies within these ancient DNA fragments we pull out of bones or sediments or other archives. So that's a great question.
In your hindcasting, what are the other missing dependent variables that you're looking at that would bring more fruit? Like the DNA, and which ones are those that are affecting your correlation that you want to get better?
Yeah. So the question was, what are we missing? How can we better improve these models? And one thing that we can do is we often talk about empirical models like these SDMs versus mechanistic models, where models are actually trying to represent the known processes of population biology and tree demography and rates of carbon sequestration and so forth. That's a whole separate field and set of models. And here we were focusing on the simpler models, partly to show these simpler models are easy to use and quicker to pull off the shelf, but they also don't work very well for these reasons I described. So other ways to go is to actually try to simulate forest stand processes and forest stand dynamics. We have some other projects that we're doing that. The other set of processes that you'd want to bring in this a bit more would be things like dispersal limitation. These SDMs pretty much assume that if the environment exists, a species can occupy it if that environment is favorable for it. But in the real world, as we saw, trees are dispersal limited. They can't just get there right away. So bringing sort of dispersal limitation into these sort of spatial models would be another thing that people are working on and doing. Yeah.
When you talk about dispersal and then movement, we're talking about something that's not just a single tree, but it's the entire environment, the insects that,
right.
So it's symbiotic relationships that also need to be,
that's right.
To do that, it has to be all the species that may be symbiotic to it in order to
yeah. Develop. That's right. And so the point about symbiotic relationships and facilitative relationships, predator-prey, a carnivore can't move north unless its prey source is moving north as well. Trees rely upon mycorrhizal fungi, and so there has to be sort of a seeding and inoculation of the ground to facilitate those trees moving northward. So you're right. This is not sort of so that's another sort of general key area is what we call sort of species interactions. And I have to say, at some point, I feel like it's sort of this is my personal perspective, it becomes almost an intractable problem, right? Because there's so many species interactions to tackle with, but at the same time, you can kind of go pair by pair. So people look at plant pollinators or mycorrhizal trees. So you can certainly kind of break it down into networks of interactions or pairwise interactions and figure out what are the crucial ones that might really limit a species moving north or facilitate a species moving north. And you can start to make some informed decisions. Okay, if we want this tree species to move north, are symbionts available? Do we need to move some of those other pollinators with it and so forth? So yeah, that is certainly another key area.
So far you talked about the climate change impact on our planet Earth.
Yeah.
The question I have is, has anybody made any study? We know if there is flooding, people try to migrate, and it's going to create a problem. How are you going to accommodate? Number of population coming, they have nowhere else to go. Probably they will come to all the Western countries. Now, does it provide an incentive for us to do more space exploration to create man-made colonies? Because we are the only country that's capable of doing it. Do you think we should put more emphasis in terms of advanced planning? Yep. Maybe we should do something about it.
And so should we be investing in space exploration and colonization of other locations? Yeah, it's yes and no. I mean, yes. I mean, part of me definitely, right? Just even leaving climate change out of the picture, you always like to think about the survival of the species long term, and you always worry about something catastrophic like a dinosaur-killing impact event that could hit us at some point, or nuclear war. There's all kinds of catastrophes you can imagine in which having a second population, a second planet, or others would be a good idea. But that said, so I support some investment in that. But that said, of course, I feel like that's I guess in general what I would say with climate change, there's no single solution, right? So that is one solution. But other solutions are much more sort of near term and we can sort of take action on right away. I would not want to sort of bet the bank on being able to colonize Mars or other planets and establish viable colonies there. I think it's a good thing to work on, but I think much of what we need to do right now is much more concrete. Putting in policies to limit our carbon dioxide concentrations, facilitating species movement. There are a lot of things we can do in the here and now that are much more, I think, realizable in the short term. One thing climate change gets political fast. I've sort of purposely steered away from that. I will comment that right now in the current there's been an administration proposal to take NASA funding and put more money into Mars exploration and less money out of our Earth observing systems for carbon dioxide monitoring, ice sheet monitoring, and so forth, that to me is a bad trade-off. I do not support that kind of managing our current crises or divesting in our current crises to invest in that kind of space exploration. So that trade-off I'm not in favor of.
Not in your field, but how will human species adapt?
Yeah, right. One of the really cool things, again, kind of on the just staying slightly on the anthropological, geological time scale of things, is to see that species. Of course, people have adapted. We're incredibly culturally and technologically adaptive, and you actually see that there's been fast human evolution. That people have found that people living in Tibet or high alpine environments have adapted those cold, low oxygen environments that people living in lowland areas haven't. So there's already not just cultural adaptation, there's evolutionary adaptation within our species as well. In general, I think there's these limits to adaptation. Certain kinds of climate change we can adapt to quite readily. We can deal with heat waves by putting in more air conditioning or setting up cooling centers in cities. We can do green roofs and white roofs. There's all kinds of adaptations we can do. We can do bigger stormwater systems for bigger flood events. That kind of adaptation is within our realm and our reach. The hard stuff is the sea level rise. That's the one that really becomes quite tricky. And sea level rise is one of these ones that's sort of gradual and incremental, but also irreversible. And so when you lose that land to the oceans, you're not really getting it back. And so places like Miami or low-lying areas, they can buy time, and the time they buy might be on the order of centuries, or certainly decades at least. They can buy time into the next century. But at some point, if climates were to change under those high-end scenarios over the coming centuries, the only adaptation would be retreat. You'd have to pull out of those areas and abandon your cities and your infrastructure in those areas. And so that's the kind of adaptation that gets quite expensive, quite disruptive, all the rest of that. So again, putting context around this, I don't worry about climate change driving species extinction, mostly at an ecological level. Certainly not, I don't think it'll drive our extinction, but it's a stressor to many other kinds of things. It's a stressor to the Middle East. You can link back to the Arab Spring being linked to a collapse in wheat production for 1 year because of a drought that hit much of Russia at that time period. So food instability, societal instability. When it comes to the human side of things, those are the kinds of things I tend to worry most about in the near to middle term. And I'll just say, climate change, I always go back and forth between optimism and despair, right? That's the kind of thing you go back and forth between. There are real worrying scenarios out there, and we try to do our best to avoid those, outline them and avoid them. There's also and I give a whole separate talk about climate change, good news, bad news, and solutions. The good news is there's rapid rates of solar installation. When the renewables ramping up is going much faster than anybody thought it would just even 5 or 10 years ago now. And even though our current political environment in the U.S. is not very conducive to progress on climate change, you kind of get the sense that that's the exception to the norm right now. Both the business sector is looking for solutions. The broader international community is looking for solutions. There's a lot of smart people working on this problem. So I tend to settle on a mid-range optimistic scenarios where I think we'll solve it, but I think a solution will be kind of getting us to 500 parts per million or 600 parts per million. We won't hit those high-end scenarios if I was to gaze at my crystal ball, but neither will we kind of stabilize where we are now. We've got a few more decades to go, is my best guess. Okay, I'd be happy to take more questions if you want to catch me afterwards. I'd really enjoyed this talk. Thank you all.